So now we're going to be looking at some related rates problems, which are pretty common for AP Physics or just calculus, AP Calculus or just calculus courses in general. So the key part to a related rate question is there's always a variable and a variable changing with respect to time, and the goal is to come up with an equation and take the derivative. That's just the general principle of what we're doing here. So water flows into a flat surface at a rate of 5 cubic centimeters per second, forming a circular puddle 10 millimeters deep. How fast is the radius growing when the radius is 10 centimeters? Okay, so what you have to relate, and what you want to do is, what I like to do is attempt to assign a name or a variable to each of these numbers and understand what is relating. So I have a circular puddle that is 10 millimeters deep. Okay, so let me kind of draw it three-dimensionally a little bit. I have a circular puddle and it's 10 millimeters deep. I'm going to make it look like a cylinder here. Okay, and it's a flat surface. Water is flowing in, so water. And so the way you want to think about it is this is volume, right? This is a flow of volume because it's cubic centimeters of water per second. So normally I would say this is volume, but this is the rate of change of volume. It's dV dt is equal to 5. And this is just telling us the height is 10 millimeters. And they're asking you they're asking you how fast the radius is growing. They're asking you dr dt is equal to what when the radius equals 10 centimeters. So what I need to do is I need to come up with an equation that relates the radius and the volume. Okay, and then then what I think about is the volume of this cylinder is how all of these variables are related. So what is the volume of the cylinder? Volume of a cylinder is the area of it times the height. In this case, I know the height is always 10 millimeters. So that's pi times r squared times, I'll do it in centimeters, which is 1 centimeter, times 1 centimeter, which is just 1, pi r squared. Okay? And then I'm going to say, well, so this is my equation, v equals pi r squared. And then I'm going to take the derivative with respect to time on both sides of the equation. It's a little like implicit differentiation, but we'll be careful. So this is so that's dv dt is the derivative of that, and then the derivative of this, well, this is pi. Derivative of r squared is 2r, but I can't just leave it as 2r. It's also times the derivative of the inside, because the inside is not t. I'm taking the derivative with respect to t, the variable t. If the inside isn't t, I have to use chain rule, and the derivative of r with respect to t is dr dt. Okay? And so then they're asking what dr dt is. I know what r is. Pi and 2 are constants, and I know dv dt. So this is 5 is equal to pi times 2 times 10 times dr dt. Or in other words, dr dt is equal to, let's see, this is 20. Well, this would be 2, and this will cancel. So 1 over 4 pi. And that's centimeters per second. Units are usually important when you're doing these kinds of things. Okay. So I have an F-22 aircraft is flying at 500 miles an hour. So it's flying this way, 500 miles per hour. That's its velocity. And you see, they've already set up x for us. So that's really equal to dx dt. It's the rate of change of x. Because if x represents where the plane is with respect to here, this is dx dt. With an elevation of 10,000 feet on a straight line path that will take it directly over an anti-aircraft gun. How fast must the gun be able to accurately track the aircraft when the plane is 1 mile away? Okay. So I want to know what happens when x is 1 mile away. That's 5,280 feet. I want to know what d theta dt is. That's what they mean by how fast it can track, I suppose, because they gave us the variable theta. So that's what I'm going to apply. It's like, how quickly does the angle need to sweep when it's that far away? So what is a variable that relates dx dt, x, and theta? Well, I just need to relate x and theta. And if you think about it for long enough, I can think tangent of theta is 10,000 over x. And so now I can take the derivative of this. The derivative of tangent is secant squared theta. Okay, but I'm taking the derivative with respect to t. But since the inside's not t, I got to do by chain rule, multiply this by d theta dt, the derivative of the inside. And this is really 10,000 x to the negative 1. So that's negative 10,000 x to the negative 2. But since this isn't t, it's some other variable, I'm going to multiply by the derivative of it, which is dx dt. And so that's equal to negative 10,000 over x squared times dx dt. So in order to solve this, I just need to find d theta dt is equal to negative 10,000 over x squared secant squared theta times dx dt. Now the problem is I don't know what theta is. I know what x is. X is 1 mile away. It's 5,280 feet. I know theta and I know dx dt, but I don't know what the theta is here. But they told you we're 1 mile away. So I can use this relation to tell us. I know that tangent of theta at 1 mile away ought to be 10,000 divided by 5,280, right? And to get rid of the tangent on this side, I would do the tan inverse of both sides. The tan inverse cancels that, so that's what theta is equal to. And so now I know what theta is equal to. I can do trigger tan inverse (62.2 degrees). Okay, so now I can do this. This 1 over secant squared, really cosine squared. So this is going to be 10,000 cosine squared 62.2 degrees divided by x with this 5,280 feet dx dt. Now dx dt is in miles per hour, so I want to convert it into feet per second, I guess, to make it like more normal units. So this is 500 miles per hour. I can use dimensional analysis to convert this into we'll say feet per second. So that's I need feet on the denominator, and I need 1 mile on the denominator to cancel out with this mile. So this is 5,280 feet in 1 mile. And then I want to convert from hours, I want seconds on the bottom. So I need hours on the top to cancel. So that's 1 hour is 3,600 seconds. So this is going to be 500 times 5,280 divided by 3,600. I get 733.3 feet per second. Okay, so then I'm going to multiply by 733 feet per second. Okay, and this is squared. Yeah, all right, good. Okay, and so I get negative 10,123 times cosine squared trig, cosine of 62.2 squared, divided by 5,280 squared times 733. I get negative 0.057, and this is in radians per second, because when we're doing trig functions in calculus, it's always in radians. That's how the derivatives and everything work, is assuming in radians. Okay, thanks for watching. If you're looking for more examples, go to my website. In there, I have free access to over 400 calculus questions that I solve and I show you step by step. So if you're interested in seeing more, please check out my website.